In the last lecture, we talked about some examples of fluid mechanics where you see fluids in action. So today we'll start with the definition of mechanics, the definition of fluid, um, and we'll see some properties of fluids and how they appear, what are their effects, how do these properties affect the flow, the behavior that we see. So let us start with mechanics. Mechanics is the study of motion and the forces which cause motion or stop the motion. Now, mechanics can be divided into kinetics, which is the study of only the motion. So, the motion involves displacement. These are the descriptors of motion: velocity, acceleration, and so on. Then we have dynamics, and further you can divide that into statics, that is study of forces acting on bodies at rest. Okay, let me write forces on bodies at rest. And then you have dynamics. And this is the study of forces and the motion of those bodies which are moving. As you can guess, kinetics can only be for bodies which are moving, not for static bodies. Now, we can further divide this mechanics based on what we are studying. Mechanics of what? So you can have mechanics of particles, mechanics of rigid bodies, and mechanics of continuous media. So we'll call that continuum mechanics. Or for plural, we can call it continua. Now you have already studied about particle mechanics and rigid body mechanics. Just to revise a little bit, what particle mechanics is: you have a particle, you have some forces acting on it, and it has some motion. Okay, then you say that summation of all the forces is equal to mass of the particle times the acceleration. If there are n forces. Okay, now for rigid bodies, let's say there is a pendulum which looks like this. This is not a point particle, so when a force acts on it, You can assume this force to be acting at the center of mass of this body. So you can convert the rigid body dynamics to point particle dynamics by averaging the forces acting on it. Although there may be some forces on a rigid body which are acting on the surface of the rigid body, such as this surface force acting on this rigid body. So what you can do is you can find a resultant of this force, you can find the net force acting on this body and the net torque acting on this body. Then you can find the rotation as well as the translation for this body. Now what is a continua? It can be either solid or fluid. What do we mean by this continua? Instead of treating a body as composed of several molecules, we assume it to be continuous. So no matter how further we zoom into this solid or fluid body, we will always have a continuous change in properties. There are no molecules here. Okay, this is the assumption. This is the hypothesis. So this is also known as continuum hypothesis, that there is a continuous change in the properties of the body. This hypothesis is valid if we are in the macroscopic regime. Okay, let's say we consider an imaginary volume, a cubical volume in a fluid or a solid, and let's start shrinking this volume to micrometer scale, to nanoscale, and even further to the atomic scale. As we decrease the size, we can plot the density versus volume of this box. At large volumes, we'll see that as we decrease the volume, the density remains constant. But at low volumes, we'll see that at very low volumes, it can happen that if it is for a fluid, then some fluid particles are coming in, some fluid particles are going out, and so on. So the density will keep on fluctuating. For the same volume, there can be several values of density. This fluctuation will increase as we decrease the volume of this box. So we'll see something like this at low volumes. And then it will become fixed. It will become a constant. And this happens at some nanometer scale. So this volume is some nanometer cube. And beyond that volume, if the experiment or the analysis involves a volume greater than this limit, then you can consider that to be continuum. Now let us discuss what are fluids and what are solids, what are gases and what are liquids. A solid is something that deforms when a force is applied to it. To a certain extent it deforms and then breaks beyond a certain stress. So if you have studied about a universal testing machine, a sample is placed in it and an extension or a shear force or a torsional force is applied to it, and the length versus delta L is measured, which is known as strain. This strain varies as you extend the rod. After a point, this rod breaks down. Which is also known as failure. However, fluids don't behave this way. A fluid continuously deforms. A fluid deforms continuously as long as a shear force is applied. In accurate terms, when a shear stress is applied, a fluid continuously deforms. Now, why this term shear is important, we'll explain that. Let's say we have a fluid in a container. Let's say it is a liquid. What kind of forces are acting on this liquid? Let's consider the boundaries. As we will derive later on, there is only pressure acting on the walls of this liquid or at any point inside the liquid, and all forces are normal to the surfaces of the liquid. Okay, so here you have normal stresses. By the way, what is stress? I can explain that here. Stress is force per unit area. If there is a force F acting on this body, acting on this surface, and the cross-sectional area is A, then the stress experienced by this surface is F by A. So stress is always defined for any surface. There has to be a surface area and a force for stress to be defined. So this is normal stress situation and the fluid doesn't flow. Now let us consider a shear stress situation. Let's say there is a wall and you have a film of liquid here attached to the wall. We can identify the forces acting on this film. For simplicity, let us assume that at the center of gravity of this film, the force of gravity is acting, mg, and along the wall there is an opposing force. We can call it force of friction between the wall and the fluid. That force F is acting. So you can see that there is a shear force. Even if the two forces balance each other, there is a shear force. If you consider any element of fluid here, this is a small element that I have zoomed into. There is a force on the left face and there is a force on the right face. So these two are equal and opposite forces. They may not be equal. Even if they are equal, there is a net shear acting on this body. After some time, this element will be deformed like this. Okay, this is known as shearing action. And in this case, we see that the film will always flow down if it is a fluid film. And of course, down or up depends on the density difference also between the film and the outer fluid. So if it is air and this is some liquid L, then it will flow down because of gravity. So this is a situation where there is flow. Therefore, if there is any shear force acting on a fluid, then there will be continuous deformation. The fluid element selected will continuously deform, and the strain is not fixed for a fixed value of shear. The strain is a function of time. Therefore, in fluids, we don't talk about strains because strain approaches infinity with time. We talk about strain rates or epsilon dot. We represent it by epsilon dot. Now let us talk about stresses a bit more. What is a stress? Generally, we denote normal stress by sigma. And shear stress by tau. So as we said that stress is force per unit area. So if let's say this is a surface and there is a force F acting on it, and let's say the surface area is A for this surface. In 2 dimensions, this is the length. Then it is force per unit area. Let us denote this F by Fn. And the shear stress is tangential force per unit area. So if there is another force Ft which is tangential to this surface, then shear stress will be Ft by the area on which this force is acting. Okay, let me ask you a question. Let's say there is a solid which has been made by gluing or attaching two pieces of solids together. So in one case, the two solids are cut like this and they are attached with the help of a glue, and in the other case, the two solids are cut like this and then they are attached with the help of a glue. And let's say the glue breaks down under shear. Okay, that is the property of the glue. Let's say that it will break down if you apply shear stress. So if you have two plates which are attached using this glue, and if you pull them like this, then it will break down. You can detach these two plates by this method, by shearing action. So let me ask you this question. If you apply the same force F to both the solids, in which case will the glue break down first? Let's say the point where you want to calculate the shear stress is this. The external geometry is the same. The point is same where we want to calculate the stress inside this body, and the forces are same. Now make a guess and then we'll go to the answer. Maybe you guessed this one, and this is correct, that this will break down first, because there is a component of shear that will appear along this plane, and because of that the glue will break down. So therefore, when talking about stresses, even if the force is same, the external geometry is same, if the area under consideration is different, then the stresses are different. So even if I don't have this glue, if I have a solid body, and if I have a single point inside this body on which I want to calculate the stress, normal stress or shear stress, then this question is not complete yet. You have to define the area as well. It will be different along that line. The stress will be different along this plane, and it will be different along any other plane. For example, in this case, in the case of these two boxes, these two blocks glued together, you have some shear stress in the first case, but you don't have any shear stress in this case. Therefore, stress is represented by a tensor, whereas force is a vector. Which means that force has a magnitude and a direction. So you can say that the force is acting in this direction or that direction. But a tensor has magnitude and two directions. Okay, so a force vector you can represent as a row vector or a row or a column vector. You can say fx, fy, fz if you are representing it in Cartesian coordinates. But a tensor, for a tensor you have to write 9 components. So in this case I'll write sigma xx, tau xy, tau xz, tau yx, sigma yy, sigma zz, where these sigma are the normal tensors, normal components, and all the tau terms are shear stresses, shear stress components. So as you can see, there are two directions here. The first subscript and the second subscript. The convention that we'll use is as follows. The normal to a surface is the first subscript for the stress component, and the direction of the force is the second subscript. So in this case, the scenario is something like this, that the force is acting on this surface in the y direction, and the surface normal is in the x direction. Therefore the stress component is tau xy. Now we can do this exercise for all the stress components, and we can see what they look like. In 2 dimensions. So we have all these surfaces pointing in all the directions. Let's say there are forces in all the directions on these surfaces. Now you have to write all the stress components. So I'll just draw these components here. So if we want to write this one, the normal to the surface is in x direction and the force direction is also in the x direction for this vector. So this component of stress is tau xx. We have already seen what this is. This is tau xy, because the normal component of the surface, the normal to the surface is in x direction, that is the first subscript, and the force is in the tangential direction, that is in the y direction. So this stress component is tau xy. Similarly, you can do this exercise for all the other components that is left as an exercise. That's all for today.